All right, so we've been talking about these different types of data, and one of the data types we've been talking about is paleo data. And so I've been asked to give a talk on how well, first of all, what paleo data is, how people have used paleo data to think about forest change in the past, and to talk a little bit about the work that I've been doing as a postdoc on PalEON. And so a lot of these ideas have been things that us on PalEON have been thinking about for a long time. And when I say us, I say that because there are several of us in the room. So there is Chris over there in the back, Jack, Jason was standing in the back of the room and seems to not be here. And who else do we have here? Yeah, there's Christy, yeah. Yeah, so a lot of us have been thinking about these ideas for a long time. And so first of all, I just want to motivate some of this. Why do we care about range shifts? And a large part of why we care about it is because work has shown that under a changing climate, we expect to see dramatic change in forest composition, in species richness, in distributions across the landscape. And so that's why these problems are critically important at this time. And so the goal of this talk, so I sort of already said it, we're going to go through what paleo data is, some history of how people have used it, and then talk about some of the challenges. So let's start with this data. So why do we use paleo data? If we want information about the modern landscape, we can go out and directly observe it. Okay? We can also use these ecosystem models to make predictions into the future and the past. But the best line of evidence that we have to really figure out what was happening in the past with respect to the ecology and the climate is this paleo data. So it's some indirect evidence of what was happening back in the past. And so when I say paleo data, typically I mean fossil pollen data, but there are other kinds of paleo data as well. So for the rest of this talk, I'll be thinking about fossil pollen data, but there are also these things called macrofossils, which are large chunks of stuff that fall into the sediment, a little bit different than pollen because they're usually heavier and the dispersal is a little bit different. And these two things, so pollen and macrofossils, can tell you different things about what kind of trees or vegetation was around a given sedimentary basin. So when we're thinking about this paleo data, we're often thinking about stuff that ends up in the sediment through these processes of dispersal and differential production and a whole bunch of other stuff, changing atmospheric conditions, et cetera. And so really the way that we get this paleo data is by taking a core in the sediment and going down the cores, like going back through time. And then we can count and identify pollen grains, and we can carbon date macrofossils to build age depth models to try to figure out how old this sample was, and that will tell us what kind of trees were on the landscape at that time. Okay, so how do we use that kind of data to learn about forest shifts? And so I want to say first that thinking about these kind of questions from a paleo perspective has a long history. And last year was the centennial celebration of pollen analysis, and that was a tribute to Leonard von Post, who was one of the first people, if not the first, to draw up what's known as a pollen diagram. So looking at changes in pollen proportions through time. And so he had this great motto, and now I'm not going to remember exactly the wording, Jack. It was think horizontally, work vertically. So already 100 years ago, he's thinking about how to use these pollen cores to understand changes in space and time. Okay, and then in the 70s and 80s, Margaret Davis started to think about how to use this paleo data, this fossil pollen data, to understand migration patterns of trees across eastern North America. And so she made these wonderful set of maps that is showing how different taxa move across the landscape. And these are based on thresholds. So we're thinking about when does a taxon first arrive, and we're defining that by being a threshold. If there's this much pollen, we say it's there. And one of the things that these maps show is that things are moving across the landscape, or at least that's what the pollen data suggests. and that things move at different rates and in different directions through time. But it's actually really hard to figure out when a species arrives on the landscape. So we might have some pollen diagrams, so a pollen proportions through time, and we might say, when does it first arrive? Is it here? Is it here? Is it here? How do we define a threshold? So that's the classic problem of defining a threshold. And so moving away from this question of species arrival, we can start to think instead about abundance patterns. So let's visualize the pollen proportions in space. And so we can do that. And when we actually compare that to trees on the landscape, we see that things don't line up. It's not a one-to-one relationship. So it's great that we can make these maps of pollen distributions moving through space and time, but that's not the same thing as trees. And so in the 1980s, Tom Webb was really one of the first people to start thinking about this. So the differences between pollen and vegetation. And so one of the issues is that, yeah.
Sorry, you're confirming this with like modern day data, like census data before?
This is.
Yeah, the left-hand map is some kind of basin area, some actual forest survey data comparing to modern pollen and like pollen.
Oh yeah. So, is that the question? Yeah. So this is for a specific species. I just didn't list it. It's actually oak. Some oak. And so one of the other issues, and well, I guess why it's not one-to-one is partly because of pollen dispersal. So for example, for hemlock, we might see the boundary of the hemlock distribution to be somewhere here, but we see hemlock showing up in pollen cores outside that range. Okay, so how do we account for that to really figure out where the trees were and when? And so we can do this by thinking about pollen vegetation models. So how does pollen relate to vegetation? And so there's a whole lot of work that has been done building up these kind of ideas about how atmospheric conditions, dispersal, differential production, and lake size affect the pollen that you end up seeing in the sediment. And so I'm just going to talk for a few minutes about this guy, Love Reveals, it's called, and steps. And so those are two pollen vegetation models. So let's predict the trees from the pollen. So we have pollen data. We want this. We're going to use a model to do that. All right, so Love Reveals, so this is following up on a lot of groundwork that was laid by people in the 80s. And one of the key ideas behind Love Reveals is that you have these different sizes of sedimentary basins. So we have small lakes and large lakes. And those represent different amounts of local versus non-local signal. Small lake, more of a local signal. Big lake, local plus regional signal. And that's just related to the size of the catchment basin, how things fly around in the air and end up in the sediment. And so I'm not going to go into details about this model, but if you're interested, I encourage you to go and check out the papers that Sugita wrote about this model. So this model requires several inputs. You have to know things about pollen productivity. So how much pollen are different trees producing? Sedimentation velocities. How fast does pollen fly around in the air? Atmospheric conditions, things like that. So these things are hard to know, very hard to know, but you need to know them to use this model. Okay. And so here comes PalEON, right? So we have from that previous model, Love Reveals, this model that actually works quite well. It works for single locations in space, and it requires a whole bunch of inputs that are hard to get. What we actually have are forest distributions across space. Okay, so there is some process of forest distribution across the space. We don't want a single point location, we want something spatial. And the reason we want that is back to this idea that we have this modern observed forests, ecosystem models, and then we have this paleo data. We would like to be able to use this paleo data to inform these ecosystem models. But how do we do that? I can't plug fossil pollen into an ecosystem model, as Christy knows very well. So when we look at this, this love reveals, so this is the model that is not spatial. It actually works quite well, and this figure doesn't really show how well it works. All I want you to take away from this figure is that these turquoise bars and blue bars are different sizes, and so that is showing how the model is adjusting. So pollen and vegetation is not one-to-one. We build a model, we do some adjustment, and some of the issues are that sometimes when we observe pollen, we predict lots of forest. Sometimes we don't really observe the pollen, but we still predict forest. And so that's one of the things that we're starting to think about here. Okay, steps. We have this previous model, love reveals, that's not spatial and requires all these inputs. We'd like to build a spatial model with a goal on estimating past forest composition with uncertainty. Okay? So we're in space and time. We would like to exploit the dependence in the data across space and time. And so we can do that. We have modern, well, historical land survey data of forest composition. We can link that to pollen records at that same point in time and build a model to calibrate. And then for past times for which we only have pollen data, we can use that model to predict our forest composition, our latent forest composition. Okay, I wanted to mention here one of the key things in this workflow is this Neotoma paleoecology database. So because we're thinking about large space-time, we really need to have this network of data, network of pollen records. And this right here, Neotoma paleoecology database, makes that possible. Okay? So this is an integral part of our workflow, and there's been lots of kind of back and forth helping develop the tools to make this data more accessible. Okay, so what do we get out of building this space-time model? So this is a Bayesian hierarchical model. What we get is this cohesive hierarchical framework that allows for this explicit accounting of uncertainty. And so not only can we make maps of how forest composition has changed back through time, we can also think about where are the significant changes. And so when I say significant, I mean statistical and ecological. And so here we can look at how hemlock, I'm not going to describe that, but that's what we can get out of it. I'm going to run out of time. And we can also start to see how things change across space. So before we were looking at single points in space, and it was hard to cut a transect across the space and really look at how a distribution of any given taxon was changing. And so our recent work has shown that we see some hemlock infilling in a hemlock range, so less of a westward expansion like we previously thought. And so this is great. This is a step towards understanding, building models like this. Okay? We have a better idea of the spatiotemporal relationship of these processes, but there are still challenges and unanswered questions. And so we're going to spend some time thinking about this in the workshop, Refugia. So we can have different kinds of Refugia. So there's a Refugia, but we don't see pollen. There's not one, but we see pollen. So how do we reconcile these issues with what we know about dispersal and other processes? Lots of people have been thinking about these migration rates estimated from pollen for a long time, and there are different ways to do that. But because it is hard to define the range edge using pollen data because of these complex dispersal processes, usually we're talking about defining how a core distribution moves across space and time as opposed to the migration of the leading edge. One of the things I wanted to mention is that One of the reasons that we're here is all the work that people have done before. I'm almost done. I'll be like 2 minutes. Thinking about why the migration rates that we see, the migration rates that we get when we look at pollen data or paleo data are so different from those that we get from molecular data. And so that paradox has been, it's called Reed's paradox, and has been written about by Jim, there in the back, and other people. And so one of the goals of the workshop is that by bringing these different data types and models together, we can start to understand why we might have been seeing this discrepancy before. And this was just to talk about some of the theory. So people have been building models to try to understand how dispersal influences how the range moves across the landscape. And when we try to fit these dispersal kernels to data, it's really hard to get data about that describes this tail of the dispersal distribution. Okay, so if we fit a kernel to data, we don't see rates like what we would expect from the paleo data. But as we increase the fatness of that tail, we do get up there. So perhaps this tail is driving this distribution. But how do we quantify that? There are two more things that I wanted to mention. One is the changing pollen-vegetation relationships. Whenever we calibrate and go back through time, we make some assumptions about how that relationship is stable back through time. We don't really know if that's true, and it's difficult to test. I'm not going to talk too much about this, but in order to figure out how old a pollen sample is, we have to build an age depth model. And we do that using dates, radiocarbon dates from macrofossils. There's a lot of uncertainty in that process, so in that dating and in fitting an age depth model, that we were trying to think about how to carry through the full analyses. Finally, for pollen data is this taxonomic issue. So some pollen grains cannot be identified to species, or if they can, some people might do it, and some people might not, depending on their ability and or the goal of the project. So when we work with these large data sets, we often have to default to the coarsest resolution or think about how to build that into the model. Computation, I just wanted to quickly mention this because it has been a huge, component of our work. When you're building these big models that have this complicated spatiotemporal dependence, they're often computationally intensive, and so you have to think carefully about dimension reduction methods or other ways that you can make this computationally feasible. Okay, and just to finish off, I guess the key message that I wanted you guys to take away is that pollen data is this rich data set that tells us something about Earth systems change in the past, and it's sort of our best way to have some indirect evidence to learn about this Earth systems change. And there's this long history of quantitative approaches in data sharing, which is kind of neat, this data sharing in the paleo field. But there's still a lot of challenges and a lot of opportunities, and I'm hoping that we can address some of those here. And so finally, I'd like to, I like this figure. This is from a Burke's paper, just talking about how to solve these methods, to solve these questions about range shifts, we can integrate across the different fields and methods, which is exactly what we're trying to do here. And I'll just end by thanking everybody, especially NIMBioS, for hosting us.